First and foremost, my name is Armando Casillas. I'm a technology researcher at Lawrence Berkeley National Lab. A little bit about myself. So I started my career as a undergrad intern at a facilities management team at University of California, Merced. So I was a mechanical engineering undergrad, and I was given a BIS, automated logic BIS, to kind of poke around. I responded to hot and cold calls, and professors super mad because their room is do you know who I am type of calls, I just kind of go in and troubleshoot VAV boxes, air handling units, and I slowly started kind of getting more familiar with mechanical systems, applying the stuff I learned in school, control systems, things like that, as well as just overall campus scale planning, campus scale operations at the chiller plant, things like that. So got my master's at UC Davis in energy systems, and there I started to talk to folks at Lawrence Berkeley National Lab through different projects, and eventually got hired there. So that's how I got here today. I work on multiple different types of projects at Lawrence Berkeley National Lab, where it's never a dull day there. Work a lot in HVAC controls, specifically commercial controls, building automation systems, also some light commercial work as well as electrified decarbonized systems, we call them, or we used to call them. Things like air-to-water heat pumps, integration with thermal energy storage. So I have a hand in all kinds of different topics around the lab. But today I'm here to talk to you guys about some of the really exciting work we're doing with energy management and information systems platforms, or EMIS platforms, and how we're using these platforms, or we're starting to use these platforms to deliver what we call the next generation of commissioning services. The future is now. So we're going to talk about that today. So learning objectives. Today you'll learn about the latest in EMIS technologies and understand how it can be leveraged to execute automated functional testing. We're going to describe the difference between open loop and closed loop tests. It could be on the quiz. These are two different types of tests we talk about for functional testing. Understand how ASHRAE's Guideline 36 implementations can be commissioned through automated functional testing. I know that's a big gap right now in the industry. And understand the benefits of automated functional testing through EMIS software, not just through EMIS software, but just generally the benefits of automated functional testing, talking specifically about EMIS software today. So here's the outline. We're going to talk a little bit about the intro and background to the project that is undergoing this work at the lab, some of the history around there, the applications for automated commissioning and functional testing through EMIS, the specifications that LBNL developed for closed loop and open loop testing in different system types, examples of the specifications and the work that we've been doing with partners or in conjunction with partners, and some work we're doing in-house in simulation to prove out some of these processes and the benefits of them. Item 5 is something I'm really excited about. We're starting to talk to folks in the industry about the value proposition around automated commissioning and functional testing. What value are they getting out of it? What are the reduction in labor hours, time, things like that. Really trying to articulate that so we could kind of synthesize all that and publish it, and something that we're really looking forward to. Well, number one, hopefully talking with more of you about, especially the ones that are doing automated functional testing. That way we can publish something with hard data that you could take to folks, and really you could start to kind of push the industry towards that. And then the last one here is commissioning for ASHRAE Guideline 36, and I'll talk a little bit about the work we're doing with that as well. So intro here, the Lawrence Berkeley National Lab has been doing quite a bit of work around characterizing the benefits of energy management and information systems. So that's what we call EMIS. EMIS are comprised of multiple different capabilities here. So number one is sort of monthly data analysis. You think sort of like your energy caps, or something that kind of brings in your data. You're able to have a dashboard for it. We also have fault detection and diagnostics tools that passively observe the data streams coming in from your building automation system and detect certain fault or fault symptoms that are happening in your building. Set points not being met, things running too long. It flags them for you. It tells you how long they've been there in your building for, and maybe even prioritize those things for you. And this last one here is a little more advanced. It's automated system optimization. These are tools that actually control aspects of your building, do things like optimal start and stop, things of that nature. we did a study through something called the Smart Energy Analytics campaign back a few years ago now. We showed that adopters of FDD tools in particular are seeing around 9% energy savings on an annual basis with an average return on investment of 2 years. So that's already pretty impressive by its own, but we know that FDD tools are still pretty hamstrung by one big thing, which is the fact that, when people use FDD tools, on average, we found that 245 faults per building are being reported by these FDD tools per month. And that's only for just AHUs and terminal units, right? So there's this flood of data that all of a sudden these folks are being exposed to, and it's just like overload, right? It's like, number one, all that stuff gets silenced. Number two, couldn't possibly be enough staff around to even address these faults in the first place. So FDD tool shows you the fault exists, but then there's this whole process that someone has to undergo to actually get that fault resolved. And this can take weeks, if not months, and that's being generous, right? So from the moment that the fault is detected, the work order gets submitted, and then finally the controls contractor or the controls tech has some time to go to the building automation system and finally clear that fault out. It can take quite a bit of time, and throughout that time there's energy being wasted that could have potentially been solved at the moment that that fault was detected, right? So we've done some fault prevalence studies over the past few years, and we actually found that the majority of the faults that exist within buildings are controls faults. So controls faults that are associated with things like schedules running too long or too short, set points being too low or too high, overrides being in place for months. These faults are not only pretty common, but also can lead to the most energy waste, especially things like scheduling. It makes sense, right? If things are running too long or too short, some systems are running 24/7. You're going to see a lot of energy waste that you could fix right away. So we think about, we're thinking now about these FDD tools, not just as passive observers, but we're really trying to get to a point where we're seeing these tools as having the ability to write back and fix the fault at the point of potential detection. So on the right side of this slide, you see the sort of spectrum of different types of applications with EMIS driven correction. On the left, you have in and out sort of processes like correcting set points, things that are maybe too low or too high that you could correct once you detect them. Over on the right side, you have supervisory control sequences, things like implementing ASHRAE's Guideline 36 treatment response sequences through an EMIS platform, or even doing things like demand flexibility if your building is enrolled in a sort of demand response program. Today, we'll be talking about the middle part of this spectrum, which is the automation of active testing. So we had a paper published a few years ago around some internal folks working on an active test to tune PID loops that are hunting in a VAV reheat box. So that's a really advanced application. Today I'll be talking about functional testing and how this sort of process can be used to automate that functional testing that folks see in commissioning workflows. So this is the future we're talking about. The project that we're doing this work in is called Fault-Free Optimal Control, so FFOC for short. And we're trying to get folks to get to this kind of paradigm where you can detect the fault, and using the same BIS using the same software that is overlaid on the BIS can be used to push a fault back, empowering like building operators or managed services providers to give them a fix-it button, right? And say immediately once the fault's detected, hey, the set point is too low, these set points are too high. Would you like to push this button to re-implement institutional standards, right? And that way you do this periodically, and just make sure that your building is operating to the intent at which you establish. So we're working with quite a bit of partners in here. This is the kind of the wide breadth of folks that we're talking to. We're talking to the software providers to see if we can work with them to implement some of these advanced processes. We're talking to portfolio managers. California State University system, for example, is a network of 20 or so campuses. They all have SkySpark implemented. So to be able to use the software that's already on site to then push the capabilities further to do some of this work it's very ripe for development, and we're really excited. And if you guys want your logo up here at some point, please talk to me, let me know, and we can maybe see how we can work together to get some of this stuff in your guys' software. So you might think, okay, well, cool, like the software is already there, right? It can already happen. Like, what's the lab doing? So the lab, we develop what we call open specifications for these strategies. So these are basically sort of generalized logical frameworks, roadmaps, you could say, around what we think are the processes, the kind of best practice processes to get these sequences or capabilities within different software environments. So this is a logical framework diagram with some pseudocode, a little bit of English language. What we think is needed in a certain software to actually enact the corrections that we're talking about. We sort of templatize this and generalize it in a way where we could take it to partner software providers or even portfolio owners who manage the software and implement this within their software environments. So now I'll be talking a little bit about how we do that with automated functional testing and commissioning. We get pretty deep here, starting here, so I'll try to make it colorful and fun and not lose you guys. But before I get there, I want to talk a little bit about how we see this application running, right? So we're thinking automated functional testing and commissioning traditionally right now is only done at certain points within a project, right? Whether it's new construction, at the end of new construction, we're about to hand that project over to a building owner, or if you have some sort of renovation happening, you do some commissioning there. Or you may have ongoing commissioning, monitoring-based commissioning. We're thinking that functional testing can be done throughout the life cycle of a building, right? This is something that has value at the beginning where you're about to hand this over to an owner, or in the aspect of periodic retesting, right? So be able to do this over the span of the building's life, every month, every quarter, to ensure that you already have the infrastructure in place, you have the points being brought into certain software, so you could just redo this over and over again. And as you redo this over and over again, you also develop a profile, right, a history of the building and its sort of its tendencies, things like maintenance history, things like that can be integrated into this process as well. So I'm getting a little bit now more into the specifics about the specifications around what we call closed loop and open loop testing. Despite the difference between open loop and closed loop testing, which I'll get to in the next slide, the generalized specification for each of them follows the same sort of process here. So the first step here is to have kind of pre-test conditions being met. If you're testing airflow control in a VAV, you want to make sure the supply fan is on, right, before you do any of that. If you're testing reheat valve operation, you want to make sure the boiler and the heating hot water pumps are on before you do that. So make sure everything's set up for your test to start. You then run through a series of functional tests, each with its own pass and fail criteria. And in some cases, in some of the tests, we have follow-on testing if a certain functional test didn't pass, right? So we have some partners that just give you sort of a fail-pass sort of a display once the functional tests are done. We have some specifications that kind of drill down a little deeper, right? So if you have a more complex system specifically, if a certain functional test didn't pass, it could be because of a multitude of different reasons. It could be for 6, 7 reasons. So running follow-up functional testing to kind of drill down and understand what it could actually be that is causing the fail test to occur allows more actionable information and allows a more targeted approach to, once the functional tests are run, the person running it can actually go to the specific component they're more confident is causing the issue. So open loop versus closed loop testing. This is sort of a nomenclature that we use, and I want to make sure you guys are clear on this. So when we talk about open loop testing, we're talking about doing a little, I call this a little more hacky than closed loop testing. You're really targeting specific components of your system. So a VAV box, for instance, you're targeting the actual damper position control override and modulating that damper to either fully closed or fully open, and seeing how that control then manifests itself in airflow, readings, things like that. Doing that allows you to have a more targeted assessment of the components and also gives you fewer plausible explanations if you do have a failed test. However, this is less palatable for a lot of people, right? If you tell somebody, hey, I'm going to go in and just hack all of your individual components, it gives people a lot of pause, not as palatable for some. For those who are a little more conservative, closed loop test is maybe where you want to go, right? And closed loop testing is defined by overriding set points specifically. So using set points to prompt a system to go into its different modes, right? So for instance, once again, going back to a VAV box, driving the set points really low to put the system into cooling, driving them really high to put it into heating, or then just making that deadband really wide to put it in deadband mode. That's exactly what I'm talking about when I say closed loop testing. This is a lot more constrained because of the ability to kind of do just the set points, but overall it's considered safer by some than open loop testing. Both are useful and effective though. So now I'm getting into like the really hairy stuff. These are some examples of the specifications that we've developed. But hopefully it kind of makes more sense because we're pairing them up with examples of some of our partners' work associated with each of these specifications we've talked about. So the first one I'm going to talk about is the open loop test suite for VAV boxes. So this is an open loop test, which once again means that we're targeting specific components. In this case, we're looking at modulating the AHU fan up and down to elicit more airflow into a VAV. But the first part of this test is looking at modulating the damper position, close and then fully open, and to determine if there's any problems with the VAV damper. For instance, if the damper is closed and the supply fan is on, and you read airflow, then you may have a problem with the leaky damper. So that's the first half of the test. The second half of the test is looking to keep the static pressure supply fan speed constant, the VAV damper constant, and then you're modulating the reheat valve and seeing how that is the system is responding to the opening and closing of the reheat valve. And that's going to be very targeted to that specific system. Anything going wrong with that, you're going to be able to pretty quickly determine that you may have a leaky reheat valve or a stuck reheat valve, or you may have problems with the supplier temperature of your air handler, right? But you could pretty well determine that with this open loop testing here. So we had a partner that did do this in parallel with us in a few of their VAV terminal units in one of their buildings. They drove the damper fully open, then fully closed, 50% open. And for each of these, they had pass-fail criteria, which I'll talk a little bit about in the next slide. They were able to do this with a total of 45 units. And then out of those 45 units, they had 14 instances of failed tests among the systems that they tested. So the pass-fail criteria in this case is, for instance, if you're modulating the damper, you're going to look to see whether or not there's a mismatch between the damper position and the command, right? So if you commanded the damper to 100%, but the position stays at 50, then there's something going on, right? And you're going to flag that as a failed test. Damper leakage, same thing. If you drive the damper to fully closed, but you still read airflow, you may have a damper that's leaking. Damper response overall is also something you want to test. Positions from 50 to 100. If you read the same airflow, then your damper may be stuck, right? Low airflow is the same thing. If you drive the damper to 100% open, but you're not getting nearly enough airflow relative to the max airflow set point, you may have a damper that's stuck slightly closed. So this is an example of the report output for this particular partner. The green text here shows that the test passed for that particular functional test. The red text shows that particular test failed, right? But as you see here, it doesn't show the actual fault, the actual potential fault. It shows the symptom, right? It says that the airflow set point wasn't met. Doesn't say why. Doesn't say Doesn't say what could be happening underneath this. We'd like to see folks get to the point where they can run follow-up testing to then drill down to the specific reason why. Which, when we talk about follow-up testing, that's what I mentioned there. So this is the example of our closed loop test suite for VAV boxes. This is looking at targeting the set points as opposed to individual components. So in this case, you're seeing the room set points driven very low to trigger a cooling mode response from the VAV box. And you have a series of functional tests that you're running through that and pass-fail criteria for that specific mode. Once you run that and you pass and fail those specific determinations, you go to the next mode, which is deadband mode, which is driving the set points very wide, so wide that the system couldn't possibly get to that temperature, right? And then you monitor the system during that period for a given amount of time. And then you drive the set points very high to heating mode. You monitor a whole different set of criteria for that. Specifically in this case, it would be a reheat valve. And then you would have a series of pass-fail criteria for that. So we have a partner doing this as well. This is a closed-loop test suite in their application here. On the left sort of box here, that's pointing to their driving their set point up and down to elicit that mode response. And then on the right sort of block pointing there, you're seeing the FDD rules that are triggered at certain stages of those mode responses as well. In addition to that, they have a report output similar to the last partner, showing green text when it's passed, red text when it's failed. One thing I'd like to point out about this particular partner is that they're doing their testing overnight, which is a great example, a great use case for automated commissioning, right? You're able to do this over several VAV boxes, tens if not hundreds of VAV boxes over the span of overnight period. But for this particular report output, you're seeing that there's details associated with each pass test and each fail test. I'll point to 2 failed tests here that were in cooling mode. The tests that failed were because the airflow set point wasn't being met. It's about 100 CFM under what it should be. And the second test happened because the AHU supplier temperature was a lot higher than it should be. So there's a reason why those two tests there failed for this particular VAV. This is another point kind of driving home this idea that if you were able to do this, able to have this sort of application in your building throughout the life cycle, you have the ability to sort of log reports or historical reports of that particular VAV or set of VAVs, from the last quarter, a few years ago, to see how those VAVs kind of performed over the span of the time that the software was installed. So this is a closed loop system test for air handling units. These systems are a lot more complex, admittedly, than VAV boxes. So I think generally this is where you're going to start to see a lot more value add for doing follow-up functional tests when something fails. But in this particular case, I'm going to show 2 examples across the rest of the presentation here around how we go about testing air handling units. The first one, though, here is around testing supplier temperature set point control. What we do is we target the supplier temperature set point, and we target the outdoor air temperature economizer lockout. And we're able to shift those up and down to then put the air handling unit in heating mode or cooling mode with outdoor or full outdoor air, or mixed outdoor air, or just full mechanical cooling at minimum outdoor air temperature. So moving the supplier temperature up really high, you trigger a heating response. Really low mechanical cooling with no minimum outdoor air. But if then you modulate the outdoor air temperature lockout set point, you can also drive the damper to give you those different modes as well. So once again, each mode has its own set of pass-fail criteria, and determining whether or not a test passed or failed. If it failed, you have additional follow-up functional tests you can do to then drive down the possibilities as to why that test failed. So yeah, this is once again the example of the supplier temperature and outdoor air control. The second test, which is the AHU static pressure reset, we'll talk a little more about in the Guideline 36 section. So this is an example of what I talk about when I say follow-up testing and the value of having these different modes. Number one, with a passive FDD tool, you would be able to pick up these faults, but only in certain seasons. If it's a heating fault, for instance, you're only going to really get that when the boiler's on, or you have heating conditions happening. But you won't get any heating faults figured out in the other times of the year. So you really, in a normal sort of test case, business as usual right now, you would really need a whole year's worth of data to get the full breadth and understand the condition of the air handling unit. But with a functional test like this, where you're driving the different modes happening, you could get that full year's picture all within a span of a few hours, right? And that's something that I think is pretty powerful here. So in this case, we're looking at a leaking heating coil valve that's affecting the AHU operation. So this system is run through its different modes, as I mentioned, to kind of get the system to respond in heating and cooling mode. And in this particular case, we had 2 cases in which the system failed a test. So you see here the different set points that are set for each of these modes. And on the second test and on the third test, we had 2 failed conditions, right? And on the right here, you see the ASHRAE Guideline 36 fault codes. This is also the APAR rules. I think what is it? Assessment performance of air systems. I forget exactly what it stands for, but APAR rules have been around for quite a bit, since 2006, I believe. Some folks at NIST developed them. And there's 2 rules specifically here that were violated during 2 of these different modes. So you see Rule 8 and Rule 13 over on the right. So what does that mean, Rule 8 and Rule 13? So fault code 8 is flagged when supply air and mixed air are equal when they shouldn't be, right? Or sorry, they should be approximately equal in operation mode where you don't have any coil valve operation. But in this case, they were different, which means that you have a possible 6 faults that could cause that failed test, right? Running the system through a different mode triggered fault code 13, which is associated with supply air temperature being above its set point in full cooling, right? And that has, you see here, that's an additional 8 faults. But the great thing about running the system in different modes and having these 2 shared faults means that these 2 shared fault codes means that you also have shared faults in between them. And the number of possible faults that are associated with both of these is reduced down to 2, right? So you either have a supply air temperature sensor error or you have a leaking heating coil valve. And now all of a sudden, running these multiple modes, you're able to dwindle down the number of possible faults and have your response be a lot more targeted, a lot more actionable running these functional tests. So when we talk about that, we're really trying to enable the second D and FTD, right? There's a lot of diagnosis going on in the industry, a lot of symptom-based sort of fault flags. But running automated commissioning, you're really able to kind of, once again, dwindle down those possible faults that are happening, and really try to make root cause diagnosis a possibility, which is really hard to do in current state. You know, folks like to do all kinds of machine learning and AI and all kinds of Bayesian optimization, analytics, all kinds of stuff to like make the accuracy better for some of these FTD tools, when you can really just be running the systems through its motions and doing this with pretty traditional, methods. So this is an example. This was a sort of simulation-based validation of what we're talking about here, where we saw out of the 19 test cases that we test in terms of underlying faults that we impose on the system, on average, we saw about an 80% improvement over just doing just one mode and detecting the fault. Doing the multi-mode analysis improved our diagnosis success rate by 80%. So there's a DOI there. I think these slides are shared, but if you want to read that paper, please be my guest. So talked about value proposition at the beginning in the intro. We're talking to partners right now about how to best characterize and the benefits of automated commissioning. One big thing that's come up is this idea of cost savings, right? So if you give an example of 100 VAV boxes, we hear, kind of the rule of thumb is about half an hour for a VAV to test a VAV. If your customer has 100 units now, and we know multiplying that kind of $175 rough per hour, you're looking at $87.50 for the whole 100 VAV boxes. With automated commissioning, number one, you could run multiple VAVs all at one time. You could do it overnight. That number drops down significantly. So by some of our estimations, we're looking at a 50 to 75% cost reduction on VAV terminal units, which to me, it just sounds like a no-brainer. It's like, let's make this happen, right? So that's, I think, a really powerful one that we're really starting to hone in on. Reduction in time, I mentioned, just because of the fact that you can run these things overnight, you can run them on a weekend, allows you to kind of use time that you wouldn't have normally been able to use to run some of this test. So this is something that we see really compelling. In the and more category, just generally, I think we're still talking to partners right now. We know that generally automated commissioning offers more cost-effective testing, as I mentioned, more comprehensive testing. There's this whole like 10 to 20% sampling sort of standard for VAV boxes. You may do it, physically, but with automated commissioning, you can get the 100% of the boxes now all of a sudden, right? This is a really funny one too, but there's the mundaneness sort of factor, right? If you're having a commissioning agent going out and commissioning 125 VAVs, by the 50th phase of VAV, they're nodding and falling asleep. They're kind of, number one, they're tired, they don't want to do it. Number two, they're more prone to mistakes if they are, kind of dozing off or whatever. Doing this through an automated fashion allows you to have more consistent testing, allows you to have more comprehensive testing, and then in some cases, through follow-up testing, you actually get more targeted responses in terms of the underlying faults that could be causing the failed testing. So we're still talking to folks about this, and specifically, if you have any thoughts or would like to discuss the benefits with us, please contact us or come to me and talk to me. I'll be around. I'll also have my contact info at the end of the slide as well. So ASHRAE Guideline 36, I think this is a grand finale here. We hear a lot from folks around ASHRAE Guideline 36. It's too complicated. Does it even work? My building operator doesn't know how to use it, so he disables it. He goes in and just overrides the set point to to 55 Fahrenheit or all kinds of stories. That's the building operator. We also hear that commissioning agents also don't know how to work. Don't know how it works either, right? So when let's say you're in a new building, ASHRAE Guideline 36 gets implemented by a controls contractor. The commissioning agent may not have a whole lot of knowledge around it, what it's supposed to be doing to even validate that it's working correctly, right? So we have a couple of applications here that I'll be talking about. The first one is a specified sort of strategy that we have in our closed loop functional testing guide for air handling units. In this case, we're looking at overriding the pressure set point at the air handler to drive the fan speed to go up at its max or go down to its minimum. If you drive the air handler to its max, the idea here is that with Guideline 36, your underlying requests are going to go down because of all the airflow you're putting into your space. Once the VAV dampers are all in deadband mode, now you could release that pressure set point. And now what you should be seeing, if the trim and respond is working correctly, is that set point is going to be driven down by the trimming going on in the Guideline 36 sequence. Conversely, if you put the set point down on minimum, all of a sudden you're going to be starving a few of your zones. Your request should go up. If you release that the supply static pressure set point, you should see that set point crawling back up to respond to that underlying request from the VAV boxes. So just sort of a spot check on, is your system trimming? Is it responding? You're not getting specifics on the rate at which it responds or trims, but you're seeing that your set point is resetting, and this is a nifty way of doing that. So this is more on the spot check sort of side. We're also looking at integrating some of our in-house tools. Specifically, we have a project called Open Building Control, which is looking at using the ASHRAE 231P standard, which specifies a control description language, right? So in the future, we're going to have these standardized control block sequences that, we can talk about Guideline 36, that basically encodes Guideline 36 in a machine-readable way and could be transferred over to anyone's software, right, or any OEM software in a way that it's standardized. It's going to be the same on one side of the tool, and when you implement it in the building, you're gonna have confidence that it works correctly. So using this sort of workflow here, what we're looking at is using that codified Guideline 36 sequence in this control description language as defined by ASHRAE 231, and comparing the expected result from that control loop with what's going on that we're observing in the building. And you're actually going to be able to follow your set point in like time step by time step and understand whether or not your system is Guideline 36 compliant, you could say, right? So compliance is around Guideline 36 is not quite set yet. Title 24, for instance, in California, is looking to set up what they call self-verification of Guideline 36 specifically. So we're seeing some applications of this. We're excited to kind of prove it out. We have some prototypes. But yeah, I think this is coming up and hopefully will be available to commissioning agents in the future. And I think it's a good application here. So with that's it for me. I just want to say, if you're interested, we want to work with you. We love talking to industry. I love coming to CX Energy, talking to folks that are actually doing the work out there. You know, people talk about research labs and ivory towers and all that sort of stuff. But I love talking to practitioners, specifically ones that are looking to kind of push the envelope, do more with their platforms. My contact there is acasillas@LBL. My PI's contact, Jessica Granderson, is there. We have a website showing some of the work we've done, some success stories, research papers. So yeah, anyway, thank you very much. And be sure to complete your session evaluation. Thank you.